In this video, we will start with Chapter 7, which is on the rules of differentiation and their use in comparative statics. Section 7.1 describes all the rules of differentiation for a function of one variable. First, we have a constant function. That means y as a function of x is equal to k. We know that the derivative dy dx is the slope of f of x, and that will be equal to 0 for a constant function. Second, we have the power rule function. This is where we have y equal to a function of x, and x is to the power of n. We know that dy dx is the slope of the function f of x, and this will be equal to n times 1, which is n to the power of x n minus 1. So to prove this function, we have our function fx equal to xn, and we want to evaluate this at the point x equal to capital N. Remember, for our derivative, we need our difference quotient, and for this we need our original point, which would be x equal to n and f of n, and we need our new point, which would be x and f of x. So our change in y will be the original y, or the new y, f of x in this case, minus f of n, divided by the change in x, which is simply the new x minus the original x. It is important to remember this function because we will come back to proofs where we require this function and we need to add and subtract certain things to get this function. So, our slope is equal to the limit as our old or our new x approaches our old x of f of x minus f of n divided by x minus n, which is our difference quotient. On the side here, what happens if n is equal to 1? This means the limit as x approaches n of xn minus n over x minus n. So this is the limit as x approaches n of what is fx equal to. Fx is equal to xn minus what is fn equal to. Simply replace x with n, so capital N to the power of n over x minus n. So if n is equal to minus 1, this limit of x to the power of n minus n is simply equal to x to the power of 1 minus n to the power of 1 over x minus n. And that is equal to 1. If n is equal to 2, it is x squared minus n over x minus n. This becomes x minus n times x This is equal to x minus n times x plus n over x minus n. What are we left with? We are left with x plus n. if n is equal to 3, we are left with x squared minus n cubed, x cubed minus n cubed over x minus n. That is equal to x minus n times x squared plus nx plus n. So we can factorize x cubed minus n cubed to x minus n times x squared plus nx plus n squared divided by x minus n. This leaves us with x squared plus nx plus n squared. So what happens? N is equal to 3, but we have x squared times x plus n squared. So our factor in our final answer is equal to n minus 1 plus nx plus n times n minus 1. In this case, we can even further generalize this function to xn minus 1 plus n to the power of n minus 2 times n plus n minus 1. Because we want this general function to be able to evaluate our slope. So what happens to our slope? This becomes the limit as x approaches n of xn minus 1 plus capital Nxn minus 2 plus Nxn minus 3, n squared xn minus 3 plus all the way n minus 1. Our limit theorems tells us if we have a sum of limits, we can limit each function. So we simply take our limits into the brackets. All the way up to the limit as x approaches n of n minus 1. Now we can evaluate the limit. So we want the limit at x approaching n. So what do? We replace our nx with n. So the first terms become n minus 1 plus n times n minus 2 plus n squared n minus 3. That should be x plus everything in between to n minus 1. This final factor, there's no x to replace, which means it's a limit of a constant, which is simply the constant itself. This gives us n minus 1 plus we have n times n. Because the base is the same, we can add the exponents. Plus n minus 1. So we are left with n minus 1 plus n minus 2 plus 1 is n minus 1 plus n 2 minus 3 is minus 1 plus everything up to n minus 1. So what are we left with? We are left with n to the power of n minus 1 plus n to the power of n minus 1. Therefore, we have n times n to the power of n minus 1 n times. So our function's limit is equal to small n times capital N to the power of n minus 1, and that is equal to our original function. We can generalize this function to the function y equal to f of x equal to some constant c times x to the power of n. The derivative of this function will be equal to the exponent times the constant, which is c times n, and then our variable x to the power of n minus 1. Again, the proof for this function, f prime x is equal to the limit as x approaches n of f of x minus f of n over x minus n. This is equal to the limit as x approaches n of c cx to the power of n minus c n to the power of n over x minus n. We can factorize the numerator by c, which is cx minus n over x minus n. Now we have a product, and we know the limit of a product is the product of the limits. The limit of a constant is simply the constant. This limit we've proved to be n times n minus 1, which means this is equal to c times n to the power, c times n times n to the power of n minus 1. So an example, if we have the function f of x is equal to 3x to the power of 6 minus 12, the slope of this function, or the derivative, will be equal to 6 times 3, which is 18, x 6 minus 1. There's no x with minus 12, which means it's a constant. A constant's derivative is equal to 0. So this derivative of this function is 18x to the power of 5.